Hello, everyone. Welcome to week 2 of the guided study groups. I hope you guys all had a great week. Sorry, just gotta check that Zoom is actually working with me this week. And we should be good. Can everyone hear me? Awesome. Okie doke. So I actually got the right book, I think. I did get the right book. So that will hopefully help us actually communicate this week, which is going to be good because that was not the case last week. So this week, I still have all of the old sections, but you guys were talking about logarithmic, exponential, like growth and decay and periodic functions this week, right? So that correlates to 1.4, 1.5, and 1.6. Correct me if I'm wrong. You can also just stop me if I start going too far, I guess. But okie doke. You do not have 1.6 for this week. So it was just the trig functions and the logarithmic functions.
Hello.
Hello.
Hi. Oh, sorry. Not muted.
Oh, you're good. Feel free to chat like via audio too if you would like to. Nobody's stopping you here. If you're more comfortable using the chat box, that's totally fine as well.
Thank you.
But sometimes it is a little bit easier to just talk, I think.
I agree. Sometimes you can, it's hard to type as quick as you can talk.
Exactly. All right, so not 1.6, no 1.6 this week. I somehow still have a schedule that said you guys did 1.6 through 1.10, which doesn't even exist in this book. So I really need to get that translated over into the new book's language. But you guys did logs and you guys definitely did trig functions this week. So we're just gonna start with that. Let's do 1.4 to start with. How did you guys find 1.4? Starting to use logs, starting to use natural logs. It's a lot of lingo, I think, that is kind of intimidating to first look at, but I hope you guys kind of started and felt a little bit better after working through them all. Let's literally just start with number 1 at the very beginning. We've got e to the ln 1/2. And then we are going to simplify that, and we are also going to simplify number 4, which is the natural log of e to the 2ab. So we're going to require some of our rules of logs to figure this out. Walk me through number 1. Maybe tell me what rule you want to use, or just tell me what you're thinking about. This is on page, please tell me that this is right. This is on page 33. definitely have the 6th edition now. You did not start logarithms.
Yeah, I was about to say, this doesn't look like something we started quite yet.
Okay, what sections did you do this week?
It was like 1.1, 1.2, 1.3, I think. And they just introduced E, but it was simplified. It wasn't it wasn't actually simplifying the equation itself. It was just like introducing it in general terms.
Hello. We also started 1.4 and 1.5. These are applications of functions to economics and exponential functions.
Okay, you guys are using Hughes Hallett, right? Deborah, is it Deborah Hughes Hallett, the calculus
Yes.
book?
Yes.
Okay.
Applied Calculus 6th edition.
Yep. Okay, that's not matching up with what I have. I says that I got the 6th edition. I got the new book this week. I'm kind of feeling like ripping my hair out right now. But we might have to, I guess, do the same snap thing that we did last week. I don't understand why. Okay, so you guys did, I thought
So
1.1 and 1.2 and 1.3 last week.
Olivia, by any chance, do you have an access to our models?
I do have access to the modules. I don't, it's telling me that you guys did 1.6 through 1.10 this week for your reading and suggested problems.
No.
Quizzes and everything are over what is a function, linear, average rate of change and relative change, application of functions, and exponential. We don't start logs, exponential growth, new function, proportionality, or periodic functions till next week.
I am so sorry, guys. I honestly do not know how this happened. I'm gonna have to email Kasha and get fixed, I guess.
Okay.
This is just not at all what I have. Under your reading and suggested problems for your module, this is fall 2019. I am in the right class. It is telling me that, I don't know if it's like a copy paste from a previous semester, but it's telling me 1.6 to 1.10, which is clearly not what's happening here.
Unless they're having
this book has a 1.10.
ahead, could they be wanting you to do a week ahead rather than that week problem?
I've always done a week behind, just to like wrap up and review the week.
Of course.
I've done this class this is like my 6th semester. So I promise you, I'm not like totally out of it.
No, you're good. Trust me.
This is just baffling to me that I'm so out of the loop somehow. Okay, so
one. So it is the 2nd week, but we are still have lesson 1 because the 1st week was introduction for us. So maybe that's why we are confusing a little bit.
Okay.
Here.
Average rate of change, exponential functions. That is what you guys did. We're gonna have to go back to the snips because I need to show you the problems that we're going to be doing, which is a little bit clumsy and not how I like to do things, but it's, I guess, how we're going to, because I, again, do not have the right book. I'm actually, Did you do concavity? Concave up, concave down, etc.?
Yes.
Okay. I'm going to okay. Can you see that? This is apparently how we're going to run our lives now. My guess is no.
No.
Now.
Yes.
Yes.
I can see.
Okay. I'm so sorry about this. I'm so sorry that this has happened again. Okay. So let's start with this. Concave up, concave down, neither. What do you guys think? What about for number 1? Yes. If I can get the pen to work. Yes. Number 2. Yep. And 3. What about number 4? It's linear. So it is neither. Awesome. Next, let's do so now it's asking us to think about increasing, decreasing, as well as concavity. And this is something that you will continue to do throughout this course. I would start by separating these points into points that are increasing and points that are decreasing. Because we're kind of asked to categorize them based on increasing, decreasing, and concavity. So which of these points are increasing? Or rather, which pairs of points is there an increase between?
I'd say A to B, D to F, H to I.
Yep. And then decreasing would be points that are not those. So between B and C, between C and D, between F and G, between G and H. All of those are decreasing sets of points. Now we can go ahead and categorize them based on concavity. What about A to B? This
Down.
chunk just here, down. And now let's think B to C.
Up. Or down. B, C, up.
B to C, yes, down. C to D?
Up.
Yep. D to E?
Up.
E to F?
Down.
Down.
F to G?
Hard to see.
Yeah, I was gonna say that one and G to H is really hard to tell.
It is pretty hard to tell, but if you think about it, like you're gonna blow up the curve essentially. Sorry, My pen is acting weird from because I'm drawing in the snipping tool. But if you think about what it actually looks like underneath there, you have a peak basically at F, and then it goes down, and then it goes back up. So if
down and up again.
Here's F, and here's G, it might be a little bit easier to think about.
FG will be down and GH will be up.
Yes.
And then HI will be up as well.
And now we have sorted them. It's probably like good to recognize that all like curves basically have this structure where if you go up, you have a maximum right here, like F we would call a maximum point. Means it's locally like the highest point like amongst the points near it. That's always going to be associated with being concave down in the near vicinity. Then there's always this point here, point G, which is an inflection point. And at inflection points, those what we basically name points where concavity changes. So we have inflection points here at G, we have an inflection point at E, and we have an inflection point at C. And basically all those points say is that, hey, we're switching from concave down to concave up, or from concave up to concave down. So that's just a little bit of like the lingo that we'll be using a little bit later on in the class to dissect basically the anatomy of a curve. And then you get down where you have a local minimum, basically the lowest point in a region, and there it's always going to be concave up, right? Because it's a minimum, all of the other points around it are going to be larger. Does that kind of make sense?
Yes, thanks.
Yes.
Awesome. All right, so we've pretty well dissected that curve. How about we try this problem? What would your first steps be to solving this problem? We're looking for an average rate of change.
Solve with the x's in the problem.
Yes. So if we think about average rate of change, we're thinking about essentially change in y over change in x, right? So our change in y is going to be f of 3 minus f of 1 over 3 minus 1. Does that make sense? Any questions about how I got that? Then we're basically just going to plug and chug. We're going to say that this is 2 times 3 squared minus 2 times 1 squared over 2. And yep, that's going to be, or is it exactly? That is 18 minus 2, yeah, it's going to be 8. So this is all going to turn out to be 8. And that is going to be our average rate of change, our delta y over delta x. Okie doke. Let's give this one a try. Can you guys read these problems? Are they like big enough for you?
Yeah, they're fine.
Okay. I didn't know. I was hoping because otherwise it would be very difficult, but okay. So we've got a particle traveling, and then we've got velocity. What is velocity? I think is an important question that we need to kind of think about. This is going to come up again and again in this class. It's going to come up in a lot of different ways in this class. So I'm going to start off basically this class by saying that velocity is the rate of change of position. Now, what does that mean? It means that as something moves, it moves with respect to both position and it moves over time. And the rate of change, how much it moves over a certain period of time, is its velocity. Correct? So we think about it, velocity is often measured in like feet per second. So that's a distance over a time. So it's the rate of change of something like moving. So we can think, I know it's specified at some point in time during this chapter, or at least it used to. They were talking about specifically average velocity. But what average velocity is the average rate of change of a position graph. And later on, you'll see that acceleration is just the rate of change of velocity. And so all of those things are very related. So it's asking about the average velocity. It gives us a time 1 and a time 2. So if we say we've got the average velocity, it's going to be equal to, what am I going to do? It's going to be equal to the position or distance, change in distance, and then the change in time, right? So what am I going to plug into here? What is going to be my D2 and D1?
Well, D2 would be 4.
Yep.
D would be 1, or yeah, 1. Because T is 0, so yeah.
And then T2 is going to be
0, right? No, 3.
These kind of correspond, yeah. So if D2 is 3, then T2 is 3, or D2 is 4, then T2 is 3. And if D1 is 1, then T1 is 0. So we're going to end up with 3 over 3. So our average velocity is equal to 1 meter per second.
Okay, that's what I got. It just didn't look like it matched up with the graph, so that's why I was a little confused.
Well, let's ask ourselves this. If I were to graph the average velocity, what would it look like? Averages are always going to be lines between 2 points.
Okay, I'm just used to like when you do like normal slope, you just go up 1 over 1 type thing. So I guess I'm simplifying it too much.
So this is exactly, it's up 3 over 3.
Okay. Okay, that makes sense.
Yep. And so this is the average velocity line, and averages are linear because you take basically 2 points. You said that I have T2, D2, and T1, D1, and I'm going to find the slope between them, and I'm going to call that slope the average velocity, correct? That's basically what we did here.
Okay, thanks.
And that is not the same thing as what is actually happening on this blue line, right? We can see that there's a difference between where those two graphs are. So the whole point of this class is to say, instead of looking at the red line, how can we look at the blue line? And so that's what we're kind of going to be working towards.
Okay, thank you.
For sure. Okie doke. Let's also do, okay. So the figure shows the amount of nicotine in a person's bloodstream as a function of time in T hours since the last cigarette. So is the average rate of change in nicotine positive or negative, and explain? What do you think about the average rate of change?
Negative, because it decreases over time.
Exactly. Next, find the average rate of change between t is equal to 0 and t is equal to 3. Give units and then interpret your answer in terms of nicotine. So we're going to be doing something very similar to what we did last time. We're going to say, right, we have 1 point here, and we have 1 point here. And so our T1 is going to be 0. Our, we'll call it N1, the amount of nicotine we have, is going to be 0.4 milligrams. This is 0 hours. Then we're going to say our T2 is going to be 3 hours. That was given to us. And our N2 is going to be, is that 0.15, would you say? Might be a little bit less, but it's about that. We have to estimate. We're working off of the graph. Next, we go ahead and specify that we're looking for an average rate of change. Or delta N over delta T. So we're going to be looking at 0.15 mgs minus 0.4 mgs over 3 hours minus 0 hours. So this is going to turn out to be negative 0.25 mgs over 3 hours. And that is what? Oh, not 9. It's less than 9. It's greater than 8. It is right, 0.08. Equal decimal point there. Negative 0.083 mgs per hour. So there are a couple of things that I did here that are going to help us interpret this. Number one is that I kept the units the whole way through. So now we know what our units are at the end, which is kind of part of the answer to the question. But I'm going to leave it up to you guys to interpret this answer in terms of nicotine. What does this mean?
The amount of nicotine decreases 8.3% an hour as time goes on.
Essentially, yeah. Yeah. We got the important fact is that it's decreasing. That's what the negative for. We know that it's changing based on how many milligrams we're losing per hour. I wouldn't say percent, because this is like an explicit number. This is 0.083 milligrams per hour. And it's, if you frame it as a percent, some information is implied. Namely that this is the amount. If it were 8.3%, we would be starting with 100 milligrams, and then it would change over time because trying to think of a good way to explain this. The best way, I think, is just to make sure that you're looking at the units and saying that this is milligrams per hour. So we're changing based upon milligrams per hour, right? If it were to be a percent, we would have to be looking at how much did we originally have, and it would not be a constant rate. It would not be a straight line. Percentages are going to be given by exponential functions, which I think you guys talked about a little bit this session, right? You at least began to touch on exponential functions. You're fine, fine. I just want to make sure that it's kind of clear that if it were to be a percent, it would look very different and it would not be linear. So the important parts is that it's decreasing, so we have a rate and we have our units. So that's what's up here. Let's start thinking about cost and revenue. So whatever section this is supposed to be, let's think about that for a little bit. Okay, we have a figure. We have a cost function and we have a revenue function. They are given to us as lines on this graph. Let's label what our fixed costs are. What are our fixed costs? Or what are fixed costs conceptually?
Well, the fixed cost is where the cost line starts, because that's that it doesn't, like, they have to pay that no matter how much of the quantity that they make.
Exactly. So this is when we have C of 0, right? This is the costs that exist when we're making 0 items. So like if we were, I don't know, running a restaurant, it would be the cost of like buying the restaurant and purchasing all of the stuff to like make a restaurant run, right? So this is the cost, and that's before even opening day. It's the cost that it makes, or the cost that exists when we're making even 0 items. Okay, what about break even? What does break even mean?
It means that we need to produce some quantity of the goods to cover our fixed cost expenses and have a 0 profit and 0 loss.
Exactly. I like how you put that, when we have 0 profit. If we break profit down into profit is equal to revenue minus costs, then to have 0 profit, our revenue must equal our costs, correct?
Yes.
So where would that point be on this line?
Intercept of R and C.
Exactly. So that's our break-even point, and this is that Q when we do break even. All right. Let's now think about when companies make a profit. What does it mean to make a profit? If we return to a profit definition?
Produce some quantity that will be over the break-even point.
Okay. Another way to think about that is to say that we have revenues that are greater than our costs, because then P will be greater than 0. So the Q where that is the case is this. And then we have to consider what it means to lose money, or that our revenue is less than our cost. We're losing money, our profit is less than 0. And that would be over here, where our cost line is indicating costs that are greater than our revenue. Does that make sense? Okay. Let's next do a company has cost and revenue functions in dollars given by C of Q is equal to 6,000 plus 10Q, and R of Q is equal to 12Q. Find the cost and revenue if the company produces 500 units. Does the company make a profit? And what about 5,000 units? So, how would I find the cost and revenue for 500 units? I would say that Q is 500. So we have C of 500 is equal to 6,000 plus 500 times 10, that's 5,000. That's 11. And then I have R of Q. That's R of 500, which is equal to 12 times 500, which is 6,000. Okay. Does the company make a profit? Nope. Because this is going to be revenue minus cost. Or and this is definitely less than 0. So we know that no profit. Now what about 5,000? Well, now we're looking at C of 5,000 is equal to 6,000 plus 50,000, or 56,000. And then we're looking at R of 5,000, which is equal to 60,000. So our profit is going to be equal to, again, our revenue minus our cost. So we will make a profit of $4,000. Okay. Our next task is to find our break-even point and illustrate it graphically. Let's graphically illustrate our cost function first. So looking at our cost function, can you tell me what the slope and y-intercept is going to be? It's going to be a line. Slope and y-intercept.
Oh, sorry, I keep hitting the wrong button. The slope for cost would be 10 and the intercept would be 6,000. For revenue, the slope would be 12. The intercept should be 0.
Perfect. So for cost, and then for this is Q, this is dollars. And then for revenue. Awesome. And then you guys just went ahead and did that and said that our break-even point is going to be Q is equal to 3,000. Awesome. Okie doke. Did you guys have any other questions with one, or I guess whatever section this is, dealing with costs, revenue, like applying all of this stuff? All right. You want to talk a little bit about exponential functions then? This is getting into exponential growth and exponential decay, which is, it can get pretty complicated and pretty confusing. So it's just kind of important to keep track of where you are. So let's use this problem to kind of break down what we're looking at. So the following functions give the populations of 4 towns with time t in years. Which town has the largest % growth rate?
1.
Yes, what is the % growth rate?
12.
Mm-hmm. Which town has the largest initial population?
2.
Yes. And our initial population is 1,000. And are any of the towns decreasing in size, and if so, which ones?
Number 4.
Yep. What's its decay rate? How fast is it decreasing in size? We're going to basically do the exact same thing we did to find the 12% growth rate. This is going to be 10% decay rate. Okie dokie. Awesome. So let's also think about this problem. I think this is a really good problem just for kind of comparing some things. We have the gross domestic product of Switzerland that was $310 billion in 2007. Give a formula for the gross domestic product in billions of dollars, T years after 2007, if G increases by 3% per year versus $8 billion per year. Let's start with $8 billion per year. What is the shape of this function? What type of function is this?
Increasing.
It is increasing. Is it like an exponential function? Is it?
Exponential function.
Is it? If we're doing $8 billion per year, dollars per year is the important part here.
This is linear function. And
Exactly. So what is my slope? My slope is going to be my rate of change, given in billions of dollars per year. So my rate of change in billions of dollars per year is 8 times how many years it is, plus my y-intercept, my initial amount.
10.
310. So kind of, is it a slant? I don't know why it ended up like that, but there is our formula for G, T years after 2007, if it's going at a rate of $8 billion per year. Now, let's think about 3% per year. Is this linear? It is not. This is going to be exponential. So we're going to have a function that looks a little bit different. What form, like, should this function be in? Like, the generic form for an exponential function. We have the decay. Right? So let's break it down. We know t is going to be our variable, but we don't know what p naught is, and we don't know what a is. What is p naught? 310. It's our initial population, our initial amount, essentially. They usually use p's for population, but this is a generic equation, and so we use it to also say just amount. What about our a? We need to first establish, are we growing or are we decaying?
Well, it says it's increasing, so it would be 1 plus the 0.03.
Precisely. So it's growing, so we know that we're going above 1, our a is larger than 1, and then we know how much by what the percent growth rate is, and then to the t. To expand on this a little bit further, which of these is going to grow faster?
%3 increase will be faster than $8 billion.
Yes. Exponential, you can see it in the graph. The exponential is going to increase far more rapidly than a linear function would. That's a really ugly linear function, but the point stands. Far more rapidly. Okay. Let's do a couple more. If I can find my page again. This is another good one, I think, just for comparing and contrasting. Okay, so we have a bunch of different cities and a ton of different graphs. I say we start with number D. Where is the population stable?
5. Number 5.
Next, I would say let's look for linear functions. I see 2 lines here. Number 3 and number 6 are both lines. Do we have any linear functions in A, B, or C?
C.
So is C going to be 3 or 6?
3.
Yes. Why is that? I would say because it's increasing and it's positive. 3 has a positive slope. C is implying that there's increasing by a certain amount of people per year. So our answer is going to be 3. Finally, we have 3 different exponential functions in this graph. 1, 2, and 4. Let's start by saying whether or not they increase or decrease. 1, are we increasing or decreasing?
Increasing.
2?
Same.
And 4.
Decreasing.
Do we have any populations in A or B that are decreasing? Nope. These are both increasing populations. So we can kick 4 out of it. So exactly. A is going to be, actually.
A is 2 because
Yeah.
it's a lower slope. 1 will be B because it's a higher percentage.
The question is, how fast are these growing? So I've got one that is growing pretty fast and one that is growing slower. And the slower one is going to be associated with the lower percent growth rate. So this is going to be 2. A is going to be 2. And B is going to be 1. Does that make sense? Because A is steeper. Or no. Graph 2 is less steep. So it's associated with A, which is the lower percentage. That's what it is. Stop keeping that. Make sure that it's all straight. Okie doke. Let's try this one. We're not going to do all of the problems. Actually, maybe we should. Let's think about this one. We're not going to do the entire graphing, but we can at least think about what this graph looks like. Okay. A 50 mg dose of quinine is given to a patient to prevent malaria. Quinine leaves the body at a rate of 6% per hour. Do you remember our nicotine question? That was going at a certain rate of milligrams per hour. This is a rate of 6% per hour. So it's going to look a little bit different.
So 50, then the A would be 94.94 to the T.
Yes, exactly. I called it A, I just called it Q, but we have the amount in mgs of quinine in the body T hours after the dose. So in order to find out how much quinine is left after 24 hours, we would say this is 50 times 0.94 to the 24 equal to Q of 24. So I'm going to plug that into a calculator because I can't just do that off the top of my head. 0.94 times 24. And then multiply it by 50. And we end up with 11.325. What are my units here? This is 11.325 what?
Milligrams.
Milligrams of quinine. Exactly. All right. Next, it asks us to graph this function. We could go ahead and calculate a bunch of different points. That is a thing that we could do, but I don't think that's really a very productive use of our time. So instead, I am just going to well, we know generally what this looks like, and it looks like an exponential decay. I went ahead and pulled up a picture of the graph, but then I realized I had to unsnip what I have snipped, and that's just not something I want to deal with right now because I will lose the question. So we have something that looks like this, right? It's an exponential decay. We start somewhere, we get lower, it goes exponentially. We could use this graph to estimate when 5 mgs of quinine remain. We start here at 50. 5 would be like way down here. We can't really extrapolate exactly what this is without more points. We do know that if this is like 10, then we'd be looking at like right here would be 11. So we know it would be much further out from 11, right? Because the greatest change, the greatest drop is going to be between 50 or between 0 and 11. Got a very steep slope there. And then the slope kind of evens out and it changes much more slowly after that point. Do you have any questions about maybe what this graph would look like? How could I find out what time it is? Actually, you guys didn't do logs yet, so never mind. You would be able to use a log in order to find out how many, what the time is when you have 5 mgs of quinine remaining. But that's a next week problem. But if you'd like to do it, we can. But it's beyond the scope of what we did this week. Any questions?
No, I'm good, but thank you.
All right. So it's been about an hour. If you guys want to keep going, we can definitely just keep doing some more practice problems. If you guys are feeling about done or don't really have any more questions, then we can call it a day. You let me know.
I'm sorry, can we have just one more exponential function example if you have a couple of minutes?
Absolutely.
Morgan is also have it.
What is there a specific type of problem that you'd like to do?
Something like the previous one with the exponential functions.
Like with graphs? Or just like the one that we just did, number 11? I'm trying to find it.
How about number 2 in the problem section in the book, where it talks specifically about growth and decay? Is that
The issue is that I have a disconnect with what you say number 2 is.
Okay, the question says each of the following functions is the amount of a substance present at time t. In each case, give the amount present initially at t equals 0. State whether the function represents exponential growth or decay, give the percent growth or decay rate. Yeah, that's what I've got.
Awesome. Okay. So, let's start with A. Let's break down A. Are we talking growth or decay?
This one's growth.
At a rate of?
7%.
And what is our initial amount?
100.
What B?
$5.3.
Growth or decay?
Growth.
And our rate is?
5.4%.
Perfect. C?
Decay.
And what's our decay rate?
0.7%. Or 7%, sorry.
Yep. And our initial value is?
3,500.
Is it clear why that's the initial value? Like, besides saying that like P naught is the initial value, does it make sense why that is the case? Because if we have A of 0, which is what we're going to say is initial, no time has passed, we end up with 3,500 times 0.93 to the 0. And do you guys know what something to the 0 power is?
1.
Exactly. So we're going to end up with 3,500 times 1. And that is what gives us. Okie doke. Let's just wrap it up with D real quick. Our initial is 12. Are we growing or are we decaying?
Decay.
At a rate of?
12%.
12%. Awesome. Any other questions? I think a lot of 1.5 is kind of getting familiar with using the P is equal to P naught A to the T equation. Just getting familiar with its parts, getting familiar with how to read it. So it seems like you guys are pretty on top of what's going on with that.
I know in later sections I will definitely have more questions than I did today.
And that's fine. It's good that this class gets off, I think, to the slow start because people can find some of this material pretty intimidating. But y'all got this, I promise. Okie doke. Well, if you don't have any more questions, then I will let you guys go for the afternoon. I hope you guys have a wonderful day, and I hope you guys have a great week. Feel free to email me with any questions that you have during the week, and I'll be sure to check them out. I will find out what's happening with my book and my canvas, because something is clearly not quite right, and I'm so sorry that it did not get figured out before today. I thought I did, but apparently I didn't. So I will get all of that straightened out for sure, and we will not have to do the snipping thing ever again. I promise. And with that, I hope you guys have a great night.
Thank you so much for taking the time. I really do appreciate it.
Of course, for sure. Thank you guys so much for coming.
Thank you.
Bye.